So we have to now prove this bound using the Donsker-Verdun lemma. So it again comes down to defining a function and using that as a lower bound on a Kullback-Leibler divergence term, and then taking the expectations to get to mutual informations. This is a recipe that I have seen over and over used in all the papers involving these bounds. So this is yet another illustration. But we get surprisingly different bounds on how the actual function is constructed. Okay, so the function that the authors constructed was like this. To construct the function, let's define the variables ji to be, let's define ji to be I if the indicator function is 0 and I plus n if the indicator function is 1, and we'll define the function bar of ji to be I plus n if the indicator function is 0 and I if the indicator function is 1. Now what we will do is we will let f of w and u, where d is the data set. So I will define a function that takes w, the weight vector, u, the collection of indicator functions, and the data set d as parameters. And I'm writing in this form because everything will be conditioned on d. That's why I'm putting d as a subscript. I will take it as lambda times, lambda is the same sort of parameter we had in the previous derivations for Russo and Zhu. I going from 1 to n, the loss function of w and z ji. So this is the sample that is actually in the training set tau. So ui is 0, then we are going to select I, and if ui is 1, we are selecting I plus n. So we take the average from 1 to n of all the elements in the training set. And then we subtract from it the average of L of W and Z J bar of I. Okay? So what we are doing is, this is the set of all the elements in the training set. JIs are selected so that JI will equal I if UI is 0, meaning that this sample was selected in the training set, and it will equal I plus n if UI is 1. So we are taking the average over all the samples in the training set, and then we are taking the average over all the samples that were left out of the training set, because this is J bar. So let me write this. This is not very nicely written. You may have difficulty later on reading it. So let me write it below. So minus 1 over n L of W and Z J I with the bar. Okay. So the bar, there is a bar here, there is no bar here. Bar means we take the complementary sample. So this is the function that they created. Okay. Note that I can also write this as lambda times 1 over n, summation of I going from 1 to n, 1 minus 2 ui times L of W and ZI, the JI now, minus L of W and ZI plus n. It's the same thing. So what this is saying is, if ui is 0, then I have L of W minus ZI minus L of W ZI plus n. Because this is in the training set, this is not in the training set. If ui is 1, then I plus n is in the training set and I is not. So this difference has to be flipped, and this trick does it. So these two are identical. In one case, we are just explicitly summing up over all the n examples in the training set and subtracting the ones which are not. In the other case, you're just adjusting the difference by this particular term. Okay. So we are going to manipulate this quantity and get to the mutual information bound. This is basically the key idea. how they developed. They started with this function rather than the function we had in Rousseau Zoo, which was the training error minus the test error. Okay, so if we now look at, let's say, the expected value of f, d, w, and u over all d, w, and u. Overall expected value, we just take the expectation over everything. This is the expected value over d, w, u. We're trying to see why this quantity makes sense. There is a lambda, so I'll just take lambda outside. It's not too important. Then I have 1 over n summation of I going from 1 to n, L, W, and Z, J, I, okay, minus 1 over n summation of I going from 1 to L, L of W, Z, J, I with the bar. I'm just rewriting the definition of f from before. The only difference is, remember, there is a bar here, there is no bar in here. This is the definition. So let's look at the two expectations one at a time. So let's consider expected value over d, w, and u, 1 over n, summation of I going from 1 to n, L of w, z, j, I. So I can write this as expected value over u, expected value over dw of 1 over n, summation of I going from 1 to n, L, w, z, j, I, given u. I can do successive expectation. First I condition over u and compute the expected value with respect to d and w, and then I average out over u. But note that if I condition on u, I actually know what the zji's are. Zji's are deterministic function of u. And basically then what we have is, this is just the average over the training set. Okay? These are all the elements in the u tells me which elements are in the training set, and I'm averaging over it. So I can replace this d by tau. Tau is basically the set of elements in the training set, which can be computed once u is known. And I can write this as EU of expected value of tau and w of 1 over n, I going from, or z in tau of L of w and z. Okay, you just average. You are basically averaging over all the elements in the training set tau now. So this is, now let's look at this inner expectation. Tau, regardless of u, has a distribution that it is sampled IID according to some PZ. You're taking the average of the training error with over this set tau. So this quantity inside is just the training error with respect to the set tau, which is sampled IID. Okay. So first there is a conditioning over u here. But if you just look at this particular quantity, what it is, tau has n training samples which are sampled IID according to PZ. And we are taking the average error here. Okay. Actually, let's write down the conditioning on u. It's not really important at this point, but we'll still do it. So we are, this is the definition of the training error with respect to the set tau. We are taking the average training error with respect to the distribution of tau and w. Okay? U is basically going to be telling us how tau was sampled in this particular step. But really the dependence of u is not important in this expectation because tau is always going to be marginally sampled IID PZ. So regardless of what u is, this quantity inside is actually a constant because it's just the average of n training samples that were generated IID. So this quantity does not depend on u as tau has a distribution which is IID-PZ. So all of this, to make the long story short, is just E in tau of W. This is the average training error you would get for your algorithm if you had n training points sample IID. So this is the first term here. So we have started with this term, so this term. And what we have shown is, if you ignore lambda for now, and if you just look at the average, the expectation of the first quantity, it is just your average training error with respect to tau and with respect to the joint distribution of tau and W. Yes. The second quantity, look at the second term. It's this quantity. Now again, we can take the expectation over u outside. Given u. Okay. Now the point here is that W does not, from the point of view of WECJI with the bar, is a fresh sample because it does not depend on W. So we can rewrite this simply as EU. When you're looking at this inner expectation, ZJI was sampled from the distribution PZ, and W is independent of it because W depends on the training set. So all of this can be written as EW and Z, where Z is independent, or I can write it like this, times 1 over n, this should be an I, not a J, I going from 1 to n, expected value of L of W, ZJI bar, and we are taking the expectation with respect to ZJI bar. The point is this quantity here is just E out of W. It does not depend on, this is basically the expectation of the loss function with respect to ZJI bar, right? ZJI bar is sampled from PZ and it's independent of the points in the training set. So this is just a definition of E out, just averaging it n times. And U is now no longer relevant. I should have a conditioning on U, but it just goes away. And all of this is EW of E out of W. So in other words, when we took the expected value over D, U, and W of FD of, what was it, W and U, what we get is lambda times expected value over tau W of E in of tau W. So the first term minus expected value over W of E out of W. And this is lambda times our generalization error function. This is the difference between the training error and the test error. Okay. So this quantity inside is really the quantity we want. This is the average training error with respect to tau and W. And this is the average test error we get. We want to bound this. So in other words, the function f was very carefully selected. You're taking the difference of these two sets, the points in tau and the points not in tau. It has a property that when you take the expectation over all random variables of interest, the training set D, the indicator functions U, and the weight W, you will basically get the quantity you want. Lambda, the constant we can play with, times gamma of p tau given W and p tau. So this is the generalization error that we want. So this function was again very careful. So in the Rousseau-Zhao proof, they explicitly had the difference between training error and test error. Here they selected the function in a way such that if you take the expectation, you still get the generalization error. So this is one of the steps. You have to make sure that when you take the expectation, you get the quantity you want. So, okay, so we have seen this. So now the next step is to consider the relative entropy quantity that we want to use. And they actually use this one, the relative entropy between Pu given Wd and Pu. Okay. And we know that this is going to be greater than the expected value over Pu given Wd Fd of Wu minus log expected value over Pu without the conditioning on W e to the Fd of W and U. So this lower bound, the Donsker-Verdun lower bound, holds for any function f, right? So we will consider the relative entropy between U given Wd and Pu. Because then when we take the expectation, we get I of U and W comma D, which is essentially what we want. We'll see why. So this quantity, so recall that we want to get this quantity on the right hand side. This is essentially the same as what we will be getting. There's a conditioning on D, but we will take care of it. So what I will do is I will first look at the relative entropy between these two distributions. U is random, W and D is fixed. Then I will take the expectation with respect to WD, okay? And that will be the mutual information between U and W comma D, and then we will see why that is the same as the other quantity. Now the trick is always to start with this quantity and lower bound it using the Donsker-Verdun lemma. And the f that we are using, so we can use any f in the lower bound, any function. The one that we are using is the one that gives us the right generalization error, which is the one that we just constructed here. So this is the function that we are going to use. So that when we take all the expectations, this is on this side, this quantity will give us the generalization error. Recall that in the second term here, in the second expectation, this is not independent. This distribution is independent of W and D. So just for sake of clarity, I will replace this by U prime. So U prime is just another copy of U sampled independently of W and D. And I'll put U prime here, just to emphasize that U prime is independent of W and D. So this distribution, here U is dependent on W and D. I can write this as just, for convenience, the expected value over U prime e to the Fd of W and U prime. So here U prime is IID Bernoulli 1/2. And in all these proofs, they really don't know how to work with the second term. So they try to simply make it basically a small quantity and when you take the expectation over the first term, you get the generalization error. So we'll see how they eliminate the second quantity first. So note that Fd of W and U prime, so we'll start with the second quantity now. This is lambda by n. I will use the second definition. I'll call this quantity delta of n, just for simplicity. So this is lambda by n, summation of n going from 1 to n, delta of n. So if I look at expected, and this is u prime. Screen. I turned off the screensaver. I don't know what happened. Still not going. So if I look at the expected value over u prime of e to the fd of w and u prime, this is expected value over u prime e to the, what do we get? Lambda by n, summation of n going from 1 to n. Okay. So here u prime of n is IID Bernoulli half, and it is independent of all the delta n's. The second term in the Donsker-Verdon lemma allows us to use the independent distribution. The first, this quantity can be easily simplified to, because it's e to the summation of exponents. The right hand side is EU prime of the summation of n going from 1 to n, or the product now, we take out from the exponent, 1 minus 2 un prime delta n. And because the random variables are IID, this goes as summation of un prime e to the lambda by n 1 minus 2 un prime delta n. Now the point here is that un prime is either 0 or 1. So 1 minus 2 un prime is either minus 1 or plus 1. Okay? And turns out that there are bounds on quantities like this. These are like, moments of a random variable. And it can be shown that for any distribution, for any x in the interval, say minus 1 to 1, for any density function, expected value of e to the lambda by n delta n x is less than e to the lambda square delta n square by 2n. There's a standard upper bound for quantities like this. It's just saying that for any random variable x between minus 1 and 1, this quantity e to the lambda by n delta n times x can be upper bounded by lambda square delta n square by 2n square. And so we can put that in. So this quantity can be easily upper bounded. So this is known as the Hoeffding's bound. It's not exactly the Hoeffding's inequality, but okay. So what we have is that the right hand side is upper bounded by summation of n going from 1 to n e to the lambda square delta n square by 2n square. Now note that since the loss function delta n is L of wzn minus L of wzn plus capital N, and this is between 0 and 1, this is between 0 and 1, so delta n square is always less than or equal to 1. Okay? So this is upper bounded by summation of n going from 1 to n e to the lambda square by 2n square, which is e to the lambda square by 2n. So the point of all this is that the second term here will simplify nicely. the second term is upper bounded by e to the lambda square over 2n. So what we have, if you rewrite the Donsker-Verdun lemma, is that the relative entropy between Pu given W and D and Pu is now lower bounded by expected value of Pu given WD, the first term, minus lambda square by 2n. To expand the first term, we have lambda times expected value of Pu given W and D of 1 by n, summation of n going from 1 to n, L of W Zjn minus lambda square by 2n. And here we are integrating out u, but we are holding W and D fixed. This is a quantity that will be some function of W and D. So we'll just call it omega. This quantity here equals omega. And since omega, lambda is a free parameter, we can set lambda to be n omega of W and D. So what we get is P of u given W and D and Pu is greater than n omega squared W and D over 2. This is now the same sort of calculation that was done in the Rousseau-Zhu bound. We got some function lower bound in terms of the parameter lambda, and then they optimize over lambda. If we take the derivative and set it to 0, you can see that this is sort of maximized when lambda is n times omega, this quantity. And when you substitute in, you get that the left-hand side is greater than n omega squared WD by 2. This is straightforward algebra, just like we had in the Rousseau-Zhu bounds. I'm going fast here. So pretty much all of this is just algebra once you have the right function. So what we have is 2 omega WD is less than 2 over n, the relative entropy between WD and Pu. So this is the bound that we have been able to obtain. So the final step is to take the expectation with respect to WD, and we will be basically done. So now we take expectation with respect to WD. We get expected value over WD, omega of WD is less than expected value over WD of square root of 2 over n d Pu given WD and Pu. I can bring the expectation inside using Jensen's argument that we discussed last lecture. And this is now the mutual information between u and W comma D. Okay? The left-hand side, you can check, the left-hand side is exactly the generalization error. It's P of tau given W. Because omega of WD took the expectation with respect to P of u given WD of the training error minus the test error. And then we are taking the expectation with respect to WD. So the function was set up so that the left-hand side is in fact the generalization error. And we have shown that this is less than 2 over n I of u and W comma D. Now note that if we apply the chain rule, I of u and W comma D is I of u and D plus I of u and W comma given D. But the first term is equal to 0 because the U sequence was selected IID independent of the D set. U and D were sampled independently. D had the 2n examples. U was IID Bernoulli half, which was sampled independently. So this quantity is 0, and so we can substitute the conditional mutual information, and that completes the proof. Okay. So this is the basic idea. So I went in a bit of rush here because most of the steps were similar to Rousseau-Zoo once you set up the function properly and know what you want the bound to be, what relative entropy to work with. If you are interested, I think there are many questions here. It is not clear to me that this is always sort of tighter than the Rousseau-Zoo bound. Like, is there a relation? Can we say that is the new bound always tighter than the Rousseau-Zoo bound? We don't know yet. At least the authors don't discuss it, and I could immediately prove it. So that's something to explore. I feel there might be a way to combine the two bounds. If one is neither not tighter than the other, they are both using Donsker-Verdon's lemma. They are starting with some surrogate function, taking the expectation, so that the expectation is the generalization error. So very similar steps, but the functions are different. Is there a way to combine them and get something tighter than the other? Another thing that is practically important is I think the size of D is too big here. We're conditioning on this data set D. D has how many? 2n examples. We are conditioning on all 2n examples. That seems to be too much for me. Can we reduce the conditioning and get something better? So we'll have to perhaps revisit how the construction is done, but see if similar tricks can be used to reduce the number of samples, the number of points we have to originally sample. So all of these are good questions for which it will be worth in. So here are some open questions. If anybody wants to do sort of a project and get some bonus points, I'm more than happy to discuss this. One is that can the two bounds be combined, be unified or combined to get a tighter bound? Can we apply the new bound to evaluate SGLD? So one of my own students is looking at this problem, the second one. So, but this is something interesting to consider. How does it differ from the previous approaches? What else? Do we need 2n samples in D in the construction of this new bound? Or can we have a more clever construction that of F that can reduce the number of samples needed? Right now they had this indicator variable, so you either take Zi or Zi plus n. It's one or the other. That's why they had 2n samples. But is there a way to somehow reduce it? I don't know, but that's just something that you can think about if you want. So anyways, I have posted all these papers online, and you are welcome to look through them. You can see what the connections are, and if you want to do a project, I'm happy to talk to you. So we'll move on now. This finishes the last part of the information theoretic bounds on generalization error. This will be a full stop for this topic, and we will move on to a new topic called Minimax Bounce. So I will post some lecture notes for this, the textbooks and so on after this lecture. But really these bounds are about proving converses. So far we have been sort of trying to develop bounds on the generalization error. This can be thought of as achievability bounds. That is, it says that if you have a training algorithm that is a small training error, then there are provable guarantees that this algorithm will perform well on test data from the same distribution, right? So this is saying that your algorithm will have a good enough performance. But you also want to sometimes say the opposite, that there is no algorithm that will require fewer than a certain number of samples to do well, right? You want to get lower bounds on the performance of an algorithm, saying no matter what you do, you will not be able to beat a minimum number of samples that are required. And that approach, at least a classical way of doing it in the field of machine learning, is through Minimax Bounce. So we'll start with that. So what we will do is, so I'll just discuss the framework today and the basic setup, and then we'll continue the discussion next lecture. So let P be a collection of distributions and suppose x1, we have some samples, x2 up to xn are sample IID from Px, where P belongs to this collection of distributions. Okay. What we want to do is, we wish to estimate some function of P. So for some function of this distribution. For example, if I look at, and let me not write Px, we'll just write it like this. So to make sure it's not a point, it's the entire function that matters, the entire distribution. So for example, we could look at the mean value of this distribution. This might be a quantity we want to estimate, the mean of the distribution. You are given n samples and you want to estimate the mean of the distribution. A simple example. Or we might want to estimate the density function itself, the entire density function. That's also perfectly valid. All of them fall in this framework. So we may want to either just estimate the mean of the data, or we may want to estimate the entire distribution. So what we do is, we let theta hat be our estimator. So we are given n points, x1 to xn. We introduce some estimator, theta hat of x1 to xn, to estimate of the quantity we want. Okay? Theta of p is the true value. If we know p, theta of p is the true value. We would know the mean and so on. So d of theta hat and theta of p is a distance metric. This is the distance between our estimate theta hat and theta p, the true value, right? And what we look at is the following quantity: expected value of d of theta hat and theta of p. So we look at the distance between our estimate and the true value, but the expectation is with respect to p, the distribution from which our endpoints x1 to xn are sampled. Okay, so here P is some fixed distribution. From P we sample x1 to xn, IID. We create an estimator theta hat. So theta hat is random. And then we take basically the expectation with respect to the distribution P when we compute this. So theta hat is a function of x1 to xn, theta of P is some fixed value. We look at the distance between these two. This could be, for example, the squared error. We'll do an example in a minute. Then we take the average expectation with respect to x1 to xn, assuming they are sampled from the same distribution P. This is what this quantity is. And then what we do in min-max is we take the supremum over all P, over all distributions, and we take the infimum over all estimates theta hat. So what we are trying to do is we are trying to find the best possible estimate theta hat, okay, given x1 to x. We don't know what P is, so our estimator only depends on the samples. We find the best possible estimate, then the nature chooses the worst possible distribution in order to maximize this particular loss function. So for any theta hat that I pick, the nature will select the worst possible distribution that will maximize this loss function, and then I am allowed to select my estimate in the best possible manner. Okay, that's the definition of the minimax risk, and this will depends on the number of samples Rn, and it depends on the overall class of densities. So P is the overall class of densities. I might know the support and so on, like some general properties of all the distributions. So it depends on that, and it depends on the number of samples. So this quantity is known as the minimax risk. Let me rewrite it here. Rn of P is the inf over theta hat, sup over P, EP of d of theta hat and theta of P. This is the minimax risk. So let me do an example just to show what this is. Suppose we have n data points that are selected IID from some joint distribution P of xy. Okay. And the question that we are interested in is, given x, what is the best estimate for y? So what we want to compute, the function that we are interested in is the regression function. So given x, we want to make the best prediction of y. Given any x, we have some joint distribution, but what we want to do is, given x, I want to make a prediction of the best possible y that is observed, the label from the distribution P of y given x. I don't have the joint distribution, so I don't have the conditional either. What I have is n samples. And from n samples, I want to make the following. Given any x, I want to make the best estimate for my label. And for that, I want to ideally compute EP of y given x of the conditional mean of y. And so in this case, my theta of P is, so if I look at theta of P, this is going to be the function MP. It's the entire function MP. For each x, I want to know what the conditional mean of y given x is. So my parameter theta of P in this case is a function. It is MP. Okay, for each x, I know what I want to compute this quantity. So if I know P, the true distribution, I can compute the conditional mean P of y given x, and this is what I'm interested in. Okay. what I would do in practice is I will let m hat of x1 to xn I can only compute some sort of given x1 to xn and y1 to yn. Should also put y1 to yn here. I can compute some sort of a regression function. Given an x, I can provide an estimate for what y will be using, say, linear regression or any other method, right? So this is what I can compute. This is what my ground truth function is, the conditional mean. And so in this case, what I want to now do next is define theta hat, the distance between theta hat and theta of p. Okay. This will be the distance between my m hat function and mp. And this can be, for example, the squared error. I look at all values of x. I look at the difference between my output. I have a hat in the wrong place. So I look at what my estimate is at that point x. I look at the ground truth, take the square of that, and integrate out with respect to x. So here the point is my output theta of my ground truth is some function, the regression, the one I can compute if I know the conditional distribution. Given the samples x1 to xn, I'm going to output some regression function, and I want to see how close is this to the ground truth. And in this case, what I'm doing is that I'm computing the pointwise difference between the estimate and the true value, and then integrating out the square. So this is, for example, my distance function. Okay, and what we are interested in, the minimax risk would in this case be inf over m hat sup expected value of p of this quantity. So for each p, I will get n samples that are used to compute m hat of x. Then I have the ground truth. I take the difference square, integrate out. Now this is a function of p. If I know p, I can compute this quantity for a given regression function. Then I take the supremum over p in my set, and then I find my infimum, the best possible estimator for the worst case distribution. So this is the minimax risk that we would be lower bounding. So if this quantity is small, or what we want to do is, given this quantity, what people often do is to find so we want to show that Rn of P is upper bounded by some un and lower bounded by ln. So remember, Rn of P is the inf over theta hat sup over P EP. Okay. This is the general definition. We want to get an upper bound and lower bound. Now getting upper bound usually is not too hard. People generally have a natural estimator in the problem they are interested in. And so if you can replace this by any estimator of interest, you will get an upper bound. If you replace the inf by any theta star, then this quantity will be less than that theta star. And then it's just a matter of computing this, which is usually not too bad. You can find the worst case p, and then that will give an upper bound. So people, when they are solving minimax risk problems, they have a natural estimator in mind and they're trying to prove its optimality. So the finding upper bounds involves just evaluating this quantity for some fixed theta hat, right? And so that is usually not the focus. Finding lower bound is where the sort of interesting sort of bounds come in. So finding lower bounds, but so our focus is on lower bounds for Rn of P. Okay. So there are basically two methods that are standard. One is there are two standard methods, and virtually all the bounds that are out there are based on these methods. One is based on what is called the Lee-Camp method, and the second is Fano's inequality. The same Fano's inequality that comes up in the proof of channel coding theorem, like proving converse for channel coding theorem, also appears in here. So these two bounds are sort of like widely used in practice in proving like lower bounds on the minimax risk. There could be other methods we know from information theory, like Shannon lower bound, that could be used in some cases, but I haven't seen too many applications of those results. So I think there is also scope of knowing what we know in information theory and applying it to some of the techniques they use in this field. Like the people here are like hardcore statisticians who have developed two or three techniques over the years and they just are very good in applying them. But I think there is scope for people from information theory community to look at these problems and see what can be done. Okay, so we'll start with the Lee-Camp method. So in this method, what we do is we select two distributions in the set P. So we are allowed to do the supremum over all distributions. We take the other extreme. We just fix two. If we fix one distribution, there is not much we can do in P and say this is what happened. There is not much we can do. So we'll do the next step. We'll take just two distributions. In Lee-Camp method, we reduce the whole set P of all feasible distributions to two distributions that are hard to distinguish in this set. We'll let delta to be the distance between theta P0 and theta P1. So this is, so theta of P0 is the parameter we want to estimate, like the mean or the regression function when P0 is the true distribution. Theta of P1 is the result we would get if P1 was the true distribution. And we are going to tell you it's one or the other. So we are being extremely generous here. So note that if you restrict like this, you are naturally giving a lower bound, right? Here we had a supremum over all P. If you restrict this to a set of two distributions, you are only going to lower bound this quantity. And hence you get a lower bound on the overall minimax risk. If you are constraining this P to be a smaller set, we cannot do as well. So we get a lower bound. We are still going to take the inf over all theta hat, but if you are going to reduce this set, you are going to get a smaller quantity. And Lee-Camp does the extreme. They just say you should reduce to only two possible distributions and make it like choose them in a careful way and sort of see what you can get there. Okay. So this is what delta is going to be. So we want delta to be the distance between P0 and P1, okay, for the parameter of interest. And now, if you look at our minimax risk, we can show, what we will show in the proof of this theorem is that this is going to be greater than delta by 4 times the integral of the minimum of P0 of x1 to xn, P1 of x1 to xn, dx1 to dxn. This is the lower bound that we will show. That delta is the distance between P0 and P1 for the parameter of interest, and then you integrate this quantity. In particular, there is an identity that can be used to show that this is greater than delta by 4 e to the minus d of P0 and P1 for any. So we can choose P0 and P1 in our design. And Licam says that if you choose this P0 and P1, your minimax risk will be lower bounded by this quantity. But recall that this delta is defined here. It's the distance between P0 and P1. And then you have the relative entropy term. So there is a trade-off in choosing P0 and P1. Okay? If you make them too close, make them very close, then this quantity, the exponent is going to be small, which is a good thing because then you're increasing the upper bound. If you make P0 to equal P1, this is going to be 0, and so you get a constant here. However, if you make them very close, then the distance between the parameters will also be close to each other, which means that this quantity will start becoming smaller. So if you make them too small, then this quantity increases, but this quantity starts becoming small. If you make them too far apart, then this quantity will increase, but then this will decrease exponentially with n. So there is a tension in choosing P0 and P1. You cannot make them very close because that will have a problem here. We cannot make them too far because that will have a problem in the exponent. So we want to select P0 and P1 to balance delta with e to the minus n d P0 and P1. And often the way we do that is that, or at least people in practice, when they have to prove these bounds, they say let the relative entropy scale as 1 over n. So we select P0 and P1 such that the relative entropy between them scales like 1 over n. So they are close to each other. As n increases, they can be made closer and closer at a rate that basically scales as 1 over the number of samples. Okay? And then with this, so because of this, we will not see like a big decrease in the exponent here. This will be like a constant. And then with this scaling, keep delta as large as possible. So you want to, at the same time, you want to select P0 and P1 so that the distance between the parameters is as large as possible. So this is the usual rule of thumb that people often use in applying Licam's bound, and we'll see some examples later on. So the key step, we don't have time to do the proof today, but the key step to lower bound Rn of p is as follows. We have inf over theta hat sup over p Rn of p. What we are going to do is we are going to replace this by inf over theta hat sup over p in p0 p1 Rn. Okay? Instead of taking all possible p's, we are only going to select 2 of them. And that is clearly going to give us a lower bound. Now this quantity here, I should not write Rn. I should write the actual expression EP d theta of P and theta hat. So I'm going, this will be here E, let me write like this. Okay. But since there are only two distributions, what we can do is we can actually write it as the max of EP0 and d theta P1 of theta hat. Since we only have two distributions, this soup is basically just max of either the first one. Did I do here? Missing one term. And the second one. Either it is EP0 here or EP1. It's just one of the two. Okay. So somehow we want to get a handle of these quantities. We still have to do the infimum over theta hat. So that is not an option. That is not optional because I'm lower bounded. Cannot plug in any theta star here, right? We want to find the best. So we want to find the best theta hat that minimizes the maximum of two quantities, right? So this looks a lot more tractable. However, how do we compute what the infimum is? Still not clear. It's an estimation problem. It depends on P0 and P1, and like it depends on the distance and so on. So the key idea in Lecamp's method and also in Fano's method is to replace the estimation problem with a detection problem. So instead of we want estimation of theta, the detection problem between P0 and P1. So this is an estimation problem. We want to find theta hat either close to theta of P0 and theta hat close to theta of P1 and take whichever one is worse. Okay, this is trying to estimate theta. And d is the distance, like the squared error and so on. This is hard to do, and Lecamp doesn't try to solve this problem. Instead, Lecamp finds a way so that this estimation problem can be mapped to a detection problem for which we can solve for the optimum theta hat, and that gives a lower bound to this problem. Okay. So how do we map? How is this mapping done? I think I only have time to explain that, and then we will continue next lecture. So imagine that we have only two variables, like two quantities, either theta is theta 0 or theta is theta 1. This is my definition of theta P0, theta P1, okay? And theta hat is some estimate lying here. Theta hat is our estimate that we get, right? So what we will do is we have some estimator, theta hat. We will convert it to the detection problem as follows. We'll define psi of x, or just call it psi, to be a random variable which equals 1 if theta is closer to theta naught, or psi 0 if theta is closer to theta naught than theta 1. And we'll call it 1 if theta is closer to theta 1 than theta naught. Okay. So we have some theta hat. This is the midpoint. The distance between them is, say, delta. This is delta by 2. If theta hat lies in this part, we will say that our estimate, the psi is equal to 0, which means P0 is the true distribution. If theta hat lies here, then we'll say that psi is 1. So we have basically now a binary decision whether P0 was a distribution or P1 was a distribution. And so we have sort of an estimation rule for theta hat, but we are going to convert it into a detection output. We are going to say psi is either 0 or 1. If psi is 0, if this condition holds, if theta hat is in this part of the interval, and psi is 1 if theta hat is in this part of the interval. Then what we will show the quantity that we want, we'll show this next lecture, that max of D or EP is going to be lower bounded by delta over 2 times the probability that's, or probability that psi is 1 under P0. So I'm going to write it like this: P0 that psi is 1 and P1 that psi is 0. So this is the probability. We'll show this next time, but this is saying that the quantity, that's the sort of the metric that we cared about in the minimax risk lower bound. This quantity is lower bounded by the probability of error we make in the decision of psi when 0 is the true hypothesis plus the probability that we make an error when 1 is the true distribution. And so this is just the Bayesian error probability, and then we will be able to find the optimal decision rule for this, and this will give us the overall lower bound. So this is the trick that, and we'll discuss this next lecture. We are out of time. So I think next week is a reading week, so we won't have a lecture. We'll resume the week after that, and we'll continue this discussion. Okay, so see you in 2 weeks.